Hi, all. So this is the recording for Dfct Unit 1. And we spoke a lot about the functions of drilling fluids in the past. This is a follow-up online version of the technical class. And let's quickly jump into the properties of drilling fluids. What is being covered to you in the class is functions of drilling fluids. I already told you it could be asked for a 2-mark question as well as a 15-mark question because that's the nature of questions. It can be dealt very seriously or it can be very simply posed for 2 marks. So when that is being asked, just stating of the functions is enough for 2 marks. Maybe max of 4 or 6 important functions which are given will fetch you 2 marks. That's enough because all the 6 or all the 4 mandate for drilling fluid functions are made in such a way it's highly technical and keyworded. So that suffices for getting full 2 marks. But if it is for a part B question or a part C question, you got to detail it out with more technicalities as what was discussed in the classes. More time was spent for these explanations, but that's the theme behind the concept, theme behind the subject itself, drilling fluid and cementing techniques. You might feel that it is taking too much time for one specific question. No, it is not. Question and answer type is for one, but what I'm handling, the methodology, what I'm following is for theme based. Handling it as a subject and handling it as a concept rather than the question and answer type. So once I go through the holistic view, the full view of handling the concept, then you'll be not having any doubt at all. As of now, we have to follow the system here in the Q&A type. So when we follow that methodology, it might give you a feel as if this is taking longer time. It's not. Once we cover 60% of the technical content of the subject, the rest 40 would take only less time. The rest 40% will take, you will find it's more repetitive content once you finish the 60% of the concept of the subject or theme of the subject. Once that is taken care of, the rest 40% will be gone in a flash moment. Now, we went through all these drilling fluids functions, and now let's start it from the properties of drilling fluids. The properties, bear it in mind that functions and properties are two different words and two different conceptual contexts. Functions, uses, properties, nature, or inherent quality of any system substance. The properties of drilling fluid can be analyzed by its physical and chemical attributes. Attributes means qualities. The major properties of fluid should be measured and reported daily in the drilling as a morning report. The one who's working as a mud engineer will have to work on all these qualities. Will have to work on all these qualities: mud weight, mud density, both being the same, interchangeable terminologies: funnel viscosity, plastic viscosity, yield point, gel strength, fluid loss, and filtering. The first one we are going through is the mud weight. Mud weight or mud density. We know what is a mass, we know what is the weight, we know what is the density. These are self-explanatory terms which we came across in schooling. The unit for mud weight or mud density interchangeably used. Weight and density are not the same conceptually, but they are interchangeably used. But we got to watch for the system of units. The unit is pounds per gallon. So let me show you a picture for what gallon is, what is a pound is, and as well as the instrument which we will be using for measuring the mud weight or mud density, which is called the mud balance, which is called the mud balance. A mud balance is an instrument which is used to measure the mud density. Now I'm shifting to the PowerPoint. You'll be able to see the PowerPoint. This is the entire schematic for drilling rig. We understood what is a drilling fluid and its operation. We saw a visualization of drilling fluid and an animation of the subsystems of the drilling rig. And then we'll be going through the drilling fluid filter cake formation as well as the drilling fluid running through the formation through the porous openings and different type of casings for different logics in specific for different set of problems. We have different type of casings with across different depths. So this is what I'm talking about. It's called mud balance. So it is an equipment which is specific. We can call it as an instrument which is used to measure the mud weight or mud density. Very specific mud density. Density is mass by volume. So one of the unit is kg per meter. So what you'll be doing here, you'll be preparing the drilling mud here, drilling fluid here, based on the chemistry provided by your company. How much is the water? How much is the clay or the bentonite? That is the weight adding material, barite, densifier, viscosifier, whatever additives you're going to add on, add it, mix it, and keep it in the stirrer, agitator. Then when consistency is obtained, you will pour the drilling fluid into this up-like structure here, up-like structure, into this mud balance. So this is how it looks like when on an elevation view. But on the top view, it looks like this. You have to open the lid and you have to pour the drilling fluid and you have to uh, wipe off the excess drilling fluid of the hole in the lid. The cover plate or the lid has got a small hole to make sure that you fill up to the lid level, up to the lid level. Fully you have to fill it. And then you have to slide the slider across and keeping this arm in the fulcrum position. You know what is a fulcrum? It's a science word. Archimedes gave it. So we know what is a fulcrum. We said that I can move the earth, but tell me where to keep it. So that's what is talking about fulcrum. Fulcrum is a point which you can have a balance and accomplish great things, even movement or no movements, or having a perfect balance. Here, the lid has got a hole, so you'll be pouring a drilling mud here, and when you place the lid, excess drilling mud will be peeping out of the hole of the lid. Wipe it off with a cloth, and then be a level glass, and there'll be a fulcrum point. This is a fulcrum point. If you do not know what is a fulcrum point, or if you've forgotten, please refer the physical balance. You'll be able to visualize it. And there is a rider. You can ride it. You can shift this here, and one of the graduating scales will give you one specific density unit, that is kg per meter. There are four densities with which you can measure here in the, this is one, and it's a cylinder with square shape. So you will be able to measure four here. So here you can see here, this is one of the scale, this is one of the scale, and here you'll be able to see another two scales. Okay, and two scales here. So if you're not able to see the units, if you say like that, I put a picture here. Next one, specific gravity, ppg, pounds per gallon, pound per feet cube. So in different system of units, in four system of units, you can measure the density with the help of the mud balance. So how does it going to keep balance here? So you pour one thing here and you are going to place the slider across the arm. Has to be balanced with the fulcrum point here, and properly weighted for the base so that uh, both the sections are in balance. How do you know that this is balance, or is it this side or that side? We have a level glass to watch. There is a bubble inside, air bubble, so you can see the bubble if it's at the center position marked marked center, then we say that it is at an equilibrium condition or it's a well balanced. So you can see in the picture here, in the level glass, you can see the bubble at the center. That means the rider here is in correct position. There is an arrow mark on the rider. You can say it's one. What is one numeral standing for? We'll see here. It could be specific gravity. What is the next scale standing for? Here, 8 point, let's say 8.4 or 8.5 or 8.6. What is it? Pounds per gallon. Pounds per gallon. So that's the basis again. That's the basis again. 8.3 pounds per gallon is the mud density for pure water. For pure water, if you could pour water here inside the cup, not the drilling fluid, what we are always talking about, if you could pour water here and close it, wipe off the water here, and then play with the rider, keeping it in the fulcrum position, and where to slide this and when to stop the slider or the rider, that will be commented by this bubble here. The bubble, if it is at the center location, that's the place you got to stop it. If it is you're moving this, the bubble will also shift. So that is taken care for the balance of the instrument. So when the instrument is in safer condition, that means equilibrium position or is in balance condition, the bubble will be at the center. That means this is the place you have to stop. Until then, you can slide upon, play, and then get things done and see what is the correct value for mud density. For water, it is going to be 8.3, and for specific gravity, it will be 1. So this is the way we can measure the mud density. Let's say this is a picture for a gallon. So you can see the cups, this is what it is. And pint means this one, quarts means this one, and gallons means 1 liter is equal to how much gallons? If that is your question, I have a next following up slide here. It's next follow-up slide here. So which talks about what is the difference between 1 pound and 1 kg. 1 pound and 1 kg. Pounds per gallon. Pounds per gallon. So we are talking about ppg here. We are talking about ppg. That's the unit for mud balance. That's the unit for mud balance. So this is the instrument. Its operation is explained by me. And now we will go back to the handouts to understand the technical contents. I've explained the operational style of the instrument or the equipment. Now let me get into technical content by reading it. Specific gravity is another system of scaling which is available in the mud balance. But we know specific gravity is another name is relative density, which is nothing but density of the substance divided by density of water, both the sample and the reference material being at same temperatures. So specific gravity usually will be no units, that because density by density, the units get cancelled. It's just a numeral. And you can also have gram per centimeter cube or kg per meter cube. Kilopascals, you can later convert it to kilopascals per meter or psi per feet. Okay. Psi per feet or pound for feet cubes. You can play with the conversion factors. You can play with the conversion factors. And now, what is the conversion for ppg? Conversion for ppg is pounds per gallon. You take the value of specific gravity multiplied by 8.3. What is that 8.333? 8.333 is the pounds per gallon of fresh water. If you pour the fresh water into the mud balance and wipe off the excess water and play with the rider and keep the equipment instrument in balance condition. How do you know it's a balance condition? The bubble at the center of the level glass will tell you it's in a balance condition across the fulcrum, and you'll be able to take the reading correct. There's no big issue. It's not a rocket science. Just keep the rider as commented by the bubble position and just mark it out. It will take 2 minutes to do this experiment. And this will be in your final year in the DFCT lab also. Next semester, you'll be studying DFCT lab. Now it's being a theory subject right now. When you perform the experiment, you will be able to understand. So the mud balance, you'll be able to get the pounds per gallon, ppg, pounds for 1 gallon. Specific gravity you'll be able to measure. You can convert that specific gravity multiplied by 8.33. It will give you pounds per gallon, or pounds per gallon is equal to kilopascals per per meter, and multiply by 1.176, and psi by feet into 0.052. So this is the conversion for converting the psi feet into ppg, kilopascals per meter, to ppg. Mud balance is the equipment which is used. It must be calibrated at the start of the job to uh, have this value 8.33 ppg. This is a standard one for the fresh water. Always calibrate it before you're running the experiment with filling fluid. Fill it with water. Check whether the instrument is showing 8.33 ppg. Then it is calibrated. That is what we call it as calibration. Checking whether the instrument is showing perfect reading is called calibration. If it is not, then we have to play with some calculations to arrive for calibrating it. A cup is filled with a sample of mud and is then balanced on the mud balance, which is calibrated to read mud weight directly. Please do not assume that I'm reading the contents, because now it's Q&A style. I'm giving my explanations then and there where it is required technically, and then I'm also reading it out. Additives. Additives are added to the main material. Main material is the bulk fluid, water. Increasing mud density should be one done with additions of weighting material. What are the weighting materials? We have already seen that in the 2 marks. Barytes, spelling BARITES, barytes, hematite, or acids, soluble calcium carbonate, and not through buildup of solids. When you want to add the weight, better choose weighting material, barite, hematite, calcium carbonate. Not add solids. What we call as solids is cuttings. If you keep on adding the cuttings, then it will be too much of solids you cannot play with. So if you want to decrease the mud density, what is the only option? It's by dilution. So coffee, let's make coffee. If you want it more thicker, add milk solids, weight adders. Okay. Or if you want it thin, pour more water. That's called dilution. What is the first point? The first point is adding an additive, weighting a material, barite, hematite, and calcium carbonate. That is milk solids added to make a very thick coffee. Or what is if somebody says they are not okay with the thick coffee, high density coffee, high weighty coffee, then you have to add hot water or hot water so it gets dilute. Same is the case with the drilling fluid. Decreasing mud density should only be done by dilution and accepting solid control practices. You can also reduce the solid control, checking the consistency, removing the content solids available. Then you can also do mm, decreasing of mud density. But the general practice is by dilution. Increasing is by weight addition. Decreasing the density is by dilution. The formula to do so is weight increase by barite. For barite alone, X is equal to 1470 into W2 minus W1 multiplied by 35 minus W2. So what is X? Number of 100-pound sacks. Sacks means the bags of cement or the mud. We know cement bags available. Sacks means the bags which are available in standard sizes of for cement or any powdered material. So drilling mud, if you are taking in barite, BaSO4, the chemical BaSO4, barium sulfite, then in one bag, standard bag, that bag is called as a sack. That bag is called as a sack. So number of 100-pound sacks per 100 barrels of mud. If you're preparing 100 barrels of mud with help of 100-pound sack or bags, do not use the word bag for easiness. I'm using it because you'll be able to understand at the start of the course. But later on, avoid the word bag and say sacks. So when you do so, number of 100-pound sacks per 100 barrels of mud is denoted by the letter X. 1470 multiplied by W2 minus W1. So this is the only, these are the only other symbols. What is W1? Initial mud weight, ppg, pounds per gallon. Please see here, this is a unit of density, pound per gallon, kg per meter cube, but it is given as a unit for weight. That's why I told you the concept, even books are treating the same way. It is also the concept behind in industries too, treating weight and density interchangeably. The mud weight or mud density unit is ppg, especially for drilling fluids in oil and gas industries. Initial mud weight is ppg, W1, and desired mud weight, that is how much weight increase you want, W2. So that if you substitute here, the initial weight you substitute here, divided by 35 minus W2 is your X. If you want to know the volume increase by using barytes, the chemical, okay, you're going to prepare this weight increase. For that, what will be the volume addition? If you want me to give a local example, yes, you're going to add, your kid is liking very thick coffee, let's say that, then you're going to add 3 spoons of milk solids to the existing coffee. Then upon addition of 3 spoons of milk powder to the existing coffee, 1 mug of a coffee, what could be the increase in volume of the entire coffee? The coffee, replace the word by drilling. Upon addition of the weight adding material called barite of this much size, X is equal to 140 W2 minus W1 divided by 35 minus W2. What is the volume increase by addition of barite to the drilling fluid? That is given by this equation. V is equal to 100 into W2 minus W1 divided by 35 minus W2. If you see here, the expressions are same. The expressions are same, and only the numerals are of difference. So it's easy to remember. But please write this one carefully because it's 100 pound sacks per 100 barrels of mud. The rest of the contents which I'm skipping through are not that much important. CS by CS ratio stands for calcium silicate ratio. Next property what we are going to see here is funnel viscosity. We have finished mud weight and mud density. Now we are moving on to funnel viscosity. What is funnel viscosity? The unit of funnel viscosity is seconds per watt. Second per UP. Watt is symbolically represented this way. The alternates are seconds per liter. Alternate units. The apparatus is called marsh funnel. Let me come back to the procedure after the showing the picture so that you will have an idea of my own explanations, and then I go to the handouts. This is what is called a marsh funnel. This is what is called a marsh funnel. So marsh funnel, it looks like a funnel, a standardized, standard, calibrated, specific dimensions built in for exclusively for oil and gas industry, especially for drilling fluid and cementing operations, a standard size. Next semester, when you come out for the laboratory, we will do this experiment by preparing the drilling fluid and measuring the viscosity. So this is called marsh funnel. One end is kept open, one end is for removing the excessive solids. You will pour it here, it will get into, and you will note down the time. You will work out with the viscosity. But for the standard, wherever you go, universal, which country you go, which laboratory you go, which college you go, if at all it is there, it's going to be the standard dimensions. The diameter, the size, the cone size, the orifice size, it's all the orifice size of the least tapering sections dimensions, all being defined according to American Petroleum Institute and ASTM, American Society of Testing Materials. We'll be pouring here the drilling fluid here. Excessive solid contents will be retained from the brim. How long it is going to take from the brim? How long it is going to take to this specific down end of orifice to pass through? So this will be poured. Adjusting how to perform the experiment. You have to keep the finger here and hold it and keep a stopwatch. When you remove the finger, how long it is going to take the fluids to pour it out into the mug. That is what is called as the marsh funnel experiment running or demonstration or operation. From that, you'll be able to find out the viscosity. So let's go back to the contents, technical contents here. Marsh funnel, this is usually calibrated to read 26 plus zero point 0.5 seconds when testing with fresh air. I'm sorry, this is a mistake here. I'm sorry, this should be tested and calibrated for water. Okay, air passes through a funnel at, at its own speed. So replace this word with water. This is usually calibrated to read 26 plus zero point 0.5 seconds. That means let's treat it roughly as 26 seconds for pouring in water, placing the finger. When you remove the finger from the down end orifice of the marsh funnel, start your stop. The time noted, how long it takes for the water. For the pure water, it takes 26. For the drilling fluid, it might take more. That is what is an indication of how much seconds per quart. Quart is the size of the funnel. The dimension, which is given by the standard bodies APA and ASTM. The simple device used for routine monitoring of viscosity. It is also performed alongside mud weight check. That means you have to measure the mud weight or mud density with the mud balance, the first property equipment, mud balance. And the second one is the marsh funnel. Both the experiments should be performed to comment on the quality of the drilling fluid or the cementing fluid. Marsh funnel readings are affected by mud weight. If it is going to be added with too much of weighting material viscosifier, then the readings of the marsh funnel will also be affected. That's what is the point, solid contents and its temperature. If the temperature is at very hot or increased temperature, then quicker is the release of the fluids through the orifice. That we know. We have seen it in Redwood viscometer as well as in Sable viscometers. The value of the marsh funnel should only be used for comparison purposes and for monitoring trends. This is an indirect indication. That's it. Okay, we're not going to make big design equations for rocket sciences from this. This is one of the tests for finding out the viscosity. This is a standard accepted practice marsh funnel experiment for funnel viscosity. What is the first property? Mud weight or mud balance. What is the second property? Marsh funnel. The third one, what we are going to see is plastic viscosity. Viscometer, especially fan VG viscometer, is one of the leading brands. Viscometer is a device used to measure the viscosity and yield point of the pipe. I have to talk about what is plastic viscosity and what is yield point. I put some contents, pictorial representations, visualizations in the PPT slide. We'll slide upon first for the PPT and then come be back here. This is a rough diagram. It doesn't match near to the reality. But anyways, this one is a slurry cup. This one is a slurry cup. And this one is a bob. It's a stationary bob. It doesn't rotate. But the sleeve which is outside, rotates. A sleeve in the shirt. What is a sleeve in the shirt? We say sleeveless shirt means it doesn't have hands. It could be a t-shirt with no hands. Okay, sleeve is an outer covering slot around an inside bob. Let's see in reality, you'll be able to understand what is a sleeve. Let's come back to this technical content after I give my explanation. Yeah. So this is what is called, let me minimize the video. This is what is called the equipment, fan VG viscometer. This is what I called as a sleeve, the outside one. And this one is the rotating cylinder. There'll be a plug to it, and there'll be a high, low, off, on switch. On switch, well, either you have to keep it just on high, low, off, on switch. Motor to keep this assembly uh, connected to the rotating cylinder. From the motor, the rotatory motion is taken here, and this is a shaft. Simply, you can call it as a shaft, and that shaft keeps rotating. Inside the sleeve or the container or the cup, thermo cup, this one, here we will pour the drilling fluid or the cementing fluid to measure the viscosity. When you keep the gearbox here, you can change the speeds, RPM range. You can raise this knob up or down. Okay, when you keep it up, you can take 3 readings. When you keep it down, you can take 3 readings. This knob, when you lift it up, 3 readings. And when you bring it down, you can take 3 readings. That's put up on the next slide. You can visualize it. You see here, when you lift up the knob and play with this switch here, that is called low of high. Low of high. Okay. So low of high, you can take 3 readings here, 200, 6, and 600 RPM. That is at down position. Sorry, 100, 3, 300. That's the down position. You see this one? When you lift up the arrow mark, the knob you lift up, it is going to give us 200, 6, and 600 RPM. This is the lower scale. The lower scale, when you keep the knob down, this knob down, when you keep this knob down, now it is a knob down position. It is not lifted. So if it is in the knob down position, the readings are 100, 3 RPM, 300 RPM. Upper position, lower position, middle position, and lower position. Okay, 3 positions are there. Now here it is, when you lift it up, you get the readings for 200, 6, and 600 RPM. 200, 6, and 600 RPM. Okay. Now let's switch on to the content to understand the technicalities. A sample of mud is placed in a slurry cup, and rotation of a sleeve in the mud gives readings which can be mathematically converted into plastic viscosity and yield point. I have to tell you what is plastic viscosity and yield point. This is called fan VG viscometer. Another type of viscometer or instrument which is used is multi-speed rheometer. Multi-speed rheometer. Readings can be obtained from 600, 300, 200, 100, 6, and 3 RPM, as I've given in the picture. So PV stands for plastic viscosity. The first inference from this experiment, plastic viscosity, and second inference is from yield point. First inference is called plastic viscosity, is measured by taking the difference between the dial reading taken at the two highest speed at 600 and 300 RPM. So what is the formula for plastic viscosity? The dial reading, the dial reading which is shown 600 minus 300, 600 reading minus 300. What is this one? Theta. It stands for shear rate. Shear rate at 600 RPM minus shear rate at 300 RPM is what is plastic viscosity, is what is called plastic viscosity. Now let me shift to the slides to tell what is the plastic viscosity here. This is a fan viscometer given by Schlumberger. Okay, how they define fan viscometer? It is an instrument to measure the viscosity of the drilling fluid as well as the cementing fluid. Let's talk about the fluid mechanics here. I'm not going to get into the power law model or the other models. What we right now require is Bingham plastic model. You might have come across this in fluid mechanics in your second years. Newtonian fluid model, Newtonian law of viscosity, shear stress to shear rate. Then if it is a straight line, if we say any fluid which is following this Newton's law of viscosity, it's a Newtonian fluid. Non-Newtonian fluid does not obey. Here we have non-Newtonian fluid, Bingham plastic model. That means when you take the shear stress on the y-axis and when you have shear rate on the x-axis, then if this is the profile, then the slope is called plastic viscosity. Slope is called plastic viscosity, and the intercept y is equal to mx plus c. M is plastic viscosity. Intercept c is called yield stress. Intercept P is called yield point or yield stress. Okay, this point, yield point. Now we talked about a fluid which obeys Newton's law is called Newton's law of viscosity or Newtonian fluid. A non-Newtonian fluid model is called Bingham plastic model. In that type of a fluid or for that type of fluid, there are two indications. One is called plastic viscosity. You can say which is an indication of how your fluid like honey, thick fluid, or drilling fluid, or lubricating oil, any substance which are in fluid condition turns into solid, mostly plastic. So that's reference is called plastic viscosity. So what is yield point? We'll come to here. What is yield point? In the slide here, this is the intercept. So if you could see the equations, we could see the equation here, Newtonian fluid, shear stress to shear rate, then this is absolute viscosity. Bingham plastic fluid, we have yield point here, that is the intercept, and slope is the plastic viscosity. Okay, slope is the plastic viscosity. So if need to know what is plastic viscosity and more inferences about what is yield point. Let's get into the slides. Sorry, let's get into the handouts. So now we have understood what is PV. PV stands for plastic viscosity given by the standard procedure fan VG viscometer or rheometers. There are readings which you can fetch from rotations, different RPMs, 600, 300, 200, 100, 6 and 3 RPMs kept at two ends, high or low. If it is at high, three difference can be taken. If it is low, three different readings at different RPMs can be taken. What is the reading which is coming out from the experiment? It is called the shear rate. Shear rate symbol is theta here at 600 rpm minus theta at 300 rpm will give you the plastic viscosity. What is plastic viscosity? It tells that honey or drilling fluid or cementing fluid viscosity is reaching to the level like plastic. It's not into terms of liquidity. It was moving, slowly shifting towards solidity. And this is my expression, this is my explanation. So shifting from fluidity state to, or even liquidity state to solidity state is what is given in terms of viscosity. That exact theme behind that is given a name called plastic viscosity. The shear rate reading at 600 rpm minus shear rate reading at 300 rpm is going to give. You have to perform is going to give you the plastic viscosity, and you have to perform this experiment at standard temperatures. Okay, they have given it as 120 Fahrenheit with the mud in a heating pump. What is yield point? The fourth property of the drilling fluid. Yield point unit is pound force by 100 square foot. Alternative is Pascal. If you want to turn the pound per 100 square foot multiplied by 0.48, you will get Pascals. The apparatus is the same equipment used for measure plastic viscosity. What is the equipment? Fan VG viscometer. FANN VG viscometer. That's why I put the Schlumberger's picture for the name's sake. Schlumberger's glossary, they are calling it as fan viscometer. What is the instrument? This is the instrument. This is the instrument. I told you three readings could be taken here. Three readings could be taken here. At low end, it is low end. It is 100, 300 RPMs. Three different rotations per minute can be tested. What could be tested? Shear rate at three different readings of RPM. Then, at high conditions, how do you play with low and high conditions? There is a knob at the bottom. There is a knob at the bottom. You keep it at high, you keep it at high, you can take bigger RPM shear rate readings. You keep it at low, this side, you keep it push the button will be at the center. You push it to high to take 3 readings RPM. And you push it to the low, you'll be able to take 3 readings of RPM. What are those 3 readings for low? 100, 3, and 300 RPM. Now, what is covered to you is the concept of plastic viscosity is covered. Let's go into the yield point. Yield point also same equipment units you have to watch for it. Yield point is the shear rate at 300 RPM minus PV. PV stands for plastic viscosity. YP stands for yield point. What is an yield point? It is an intercept. In the graph for the Newtonian fluid Bingham plastic model, the slope is the PV plastic viscosity and intercept M for the equation y is equal to mx plus c straight line equation. M is the slope and c is the intercept. C stands for yield point. The point plastic viscosity increase indicate the solid control equipments are running efficiently. Okay, or you can say inefficiently. It comments about whether it's efficiently running or inefficiently running. If that is what is the handout comment, then let me give you a low technical insight into it. Let me give you a technical insight into it. A low plastic viscosity means drilling will be rapid. That means the low plastic viscosity means what? It means that it is still in the fluidity range, liquidity range. So the drilling will be faster. If the high plastic viscosity of the drilling fluid is used, then there is a presence of more solids, excessive solids, and it's highly viscous. Then the what action you have to take, you have to dilute much. If the highly viscous fluid, that means high plastic viscosity, then you have to change your motor configurations or the speed or the gearboxes, whatever transmitting means, you have to play accordingly. So that's the logic behind yield point. That's the logic behind yield point. What is gel strength? Gel strength is also same as yield point. The unit for gel strength is also same as yield point. Alternatives also same, but the apparatus is also same. EG viscometer, 6-speed viscometer, they are saying 6 RPMs. There are 2 readings for gel strength. You can also take 2 more readings, which refers conceptually to the gel strength, which is nothing but the strength of the fluid to become a gel. Puts it simply, the strength of the fluid to become like a jelly or a gel at, at specific time duration. Let's say it's for 10 seconds and 10 minutes with a speed of viscometer set at 3 RPM. It must be at the 3 RPM and it must be the 3 RPM and the fluid must be remained static prior to each test. The highest peak reading will be reported. That means there'll be deflection seen in the needle. The needle starts growing. Then you should note down the maximum point of the achievement of the reading. Why? Because the needle gets deflected back to another position. So when you're taking readings, what you have to do, you have to keep the instrument in the static condition, and then when you're going to take the reading when the of the shear rate theta at some specific rotation, what you got to take it the maximum deflection of the needle. Maximum deflection will be, say, let's say 11, 14, but it will drop down sooner. It will drop down sooner based on the speed. So you have to consciously watch for it. Then you'll be able to get the readings. The gel strength, what it tells or it quantifies the thixotropic behavior of the fluids. Thixotropic behavior. What did I told you in 2 marks thixotropic? It is a property of becoming less viscous when a fluid is exposed to a shear or applied stress. Let's take an ointment. Let's take honey. Let's take a cream and then put a spoon into and stir it. When you put stress to it, what's happened to the viscosity? Viscosity will get reduced, obviously. That nature is called thixotropic. If you want me to give a very fine example have put a visualization for you to better understand what is thixotropy. Let's get into the example here. Gel strength can be measured as an ability of a colloidal dispersion to develop a gel or retain as a gel itself. You guys know this Heinz uh, ketchup, or in our country we have Kisan ketchup, tomato ketchups, in plastic bottles as well as in bottles. If you take the plastic bottles and then if you're able to shake it or press it, then until then the fluid will not be out. When you press it, when you apply stress, when you shake it, when you vibrate it, then the ketchup liquefies and flows. Then the ketchup liquefies and flows. Until then, there is no flow. What does it mean? The fluid, which is upon application of stress, the viscosity changes. That is what is called gel strength. Once the vibration stops, the ketchup returns to its original viscosity. You don't press it, then the same viscosity. Until you press it, you'll be able to see fluidity happening. So this concept or theme behind that is called gel strength. The ability of a ketchup, tomato ketchup, to behave or retain as a gel to resistance, offer resistant to shear, is called gel strength. So this is what for the drilling fluid also the same condition. A drilling fluid, when it is rotating, because of the hydrodynamics of the drill bit and the fluid present there, then the chances are the drilling fluid could become like a gel. What is the parameter or the concept with which we are going to measure? It is the gel strength. How to do this experiment? We'll be performing it in the next semester. But theoretically, I'm talking about it. It is uh, it is running at 3 RPM and noting down the theta reading. Theta reading. Theta reading is shear rate. The shear rate reading for 10 seconds and for 10 minutes. Two readings you have to take for 10 seconds and 10 minutes. Pour the drilling fluid into the fan with viscometer. Let it run. So keep the knob from zero position to uh, low positions, that is 3 RPM. Raise the knob. Then you'll be able to wait for 10 seconds, note down the reading, that is theta 10 second. And 10 minutes, if you wait, you'll be able to see the 10 minutes and then you'll have to take the reading. What reading? The deflection, maximum deflection. It will give you the highest peak reading is reported as the Gill strength. As of now, it's time. So let's break it here and be for the same sessions in the next clipping. Mhm. We are now back to the question called properties of drilling fluids. We're now seeing this fluid loss and filtration. The unit for that is milliliter per 30 minutes, or you can switch on to the system as given there. Bottom full temperature and can be for PSI or 500 PSI to fixed temperature. HP stands for high temperature, high pressure conditions. The same experiment we conducted for HTF, high pressure, high temperature well conditions. Then that experiment will be called as APA filtration loss, HTHP. This is a basic experiment conducted to measure the property of fluid loss and filter rate with the help of an instrument called APA filtration apparatus. The given a demonstration or will be performing the experiment the next semester when you are on the Dfct level. Filter cake thickness is measured in 1 by 32. Yes. This again. Filter cake thickness is measured in 1 by 32 inches. So what we are talking about is the fluid loss and the filter cake, which is done in the experiment, APA filtration loss. It can be performed at HT, HP, well conditions also. How does this experiment look like? Try to share a screen right now. Solutions. Now let me share it again. This is what the experiment unit looks like. Filtration loss. This is a cylinder at HPHT conditions. High pressure, high temperature conditions. At the bottom, you have a graduated cylinder. And this is a rough diagram for it. You can see here, it's connected to high pressure assembly here. From here, the pressure is put on to the cylinder. Inside the cylinder, you'll be having the drilling fluid or the cylindrical fluid. And at the bottom, there'll be an aperture on orifice through which the fluids could pass through, filter placed on top of. The experiment is conducted to find out how much is the filtration loss passing through the filter paper, standard filter. So the water liquid which passes through is called the filtrate, and the cake which sits on the top is called the filter. Filter cake sits on the filter paper, and the filtrate is passing through the orifice as well as the filter paper and it's collected in the graduates. Perform the experiment under high pressure, high temperature conditions. This is being simulated to industrial setup or well being posed to HPHT. This is a very simple experiment here. Just tell the fluid loss in the filter. So now we see the diagram. Let's get into the technical notes. What we have at our step here. So do have a cell, a cylinder. Once you fill the cell with drilling fluid, and inside the cell you'll be placing a filter paper, and you'll apply the drilling fluid on top of it with pressure or without pressure. It's up to you when you perform the HPHT conditions with pressure. If not at normal, you close it and then you leave it to atmospheric pressures or high pressure condition. So what will happen to the fluid? The fluid will pass through the paper, pass through the filter paper and get into the aperture. Aperture is nothing but a hole, orifice, through which the filtrate will pass. The solids which are accumulating on the filter paper is called the filter cake, and the liquid which is passing through is called the filtrate and is collected in a graduated cylinder. Sorry for the spelling today. It is not granulated cylinder. It should be read as graduated cylinder. You guys know what is a graduated cylinder. The filter cake is usually measured and it will be 2 mm thickness minimum to maximum 12 mm thickness. High pressure, high pressure, high temperature conditions can be simulated in this experiment. When the temperature is greater than 200 degrees Fahrenheit and the pressure conditions, what could be achieved in the laboratory being related or simulated to high temperature conditions of the reality, the EMP context. Other properties are pH, alkalinity, cation exchange, electrical conductivity, lubricity, and porosity. We'll talk about these concepts again in the last page of the. So in simple words, this is the last property with the cake and fluid loss. So why we do conduct this experiment? To find out how quickly the film rate is passing through the filter cake across the porous formation. If all the water is being lost, all the drilling fluid is being lost, we're going to use air. So we will not let that to happen. We want a good cake to be built up, which will allow only controlled fluid loss to happen in the porous form. If every fluid is not coming back to the annulus and is running somewhere else, we call it as loss circulation or passing into deep zones. We don't want that to happen. That is why this concept is established or demonstrated or understood with the a setup called APA filtration loss. Having covered all the six properties from building fluid, we are moving on to the next. Functions and properties of cement. Functions of cement. Before getting into functions of cement, let's get into the very classic definition of what a slurry is. A slurry of cement is nothing but it's cement powder plus water and some additives or chemicals which are pumped down to the annulus, to the steel casing, to the annulus. It is actually pumped to the steel casing to the annulus and sets between the annulus, if it is the outermost casing, between the outside of the casing and inside of the valve. Accordingly, the annulus keeps different depending upon what casing to what casing and what is the annulus between them. The functions of cementing process are restrict the movement between permeable zones. So if all the fluids are being lost, then it creates a deep zone. That's the seventh point here. Sealing of zones of loss circulation of deep zones. You don't want the cementing fluid to run off. You don't want the cementing fluid to run off into the porous formations, and we don't want the concept of having suffering from financial loss. So we call that as a loss circulation. Call that as a loss circulation or deep zones. The first of the functions of cement is restriction of a fluid movement between permeable zones. We don't want the fluid to move on from the permeable formations to get into the annulus and attack the casing. So that is why we put this cement there. We want to restrict the movement and we want to offer mechanical support. Fourth point is also support for the wellbore. And third point is to protect the casing from corrosions. So if there is a gap in between the outside of the casing and inside of the wellbore, and chances of the fluids are coming in, it could corrode and as well as corrode in the long run. So we don't want this way to move with cements. And the last one is to control the formation pressure. If there is a mechanical stability, then fluid stability also will be ensured. That means if it is strong, it is going to save the casing and it's going to create a well-bore stability there. And then the whole well-bore stability can be achieved. And thereby, the blowout skids to be managed. How come this is all possible? If it is a quickly settling cement. The cement, fifth point, cement which is got a quickly forming nature of a gel. So if the gel forms quickly and settles and hardens, then the job is taken care of. So finally, the sixth point is also to ensure that the casing of the shock loads. We covered all the 7 points and then move on to the properties of cement slurry. We have discussed all these properties of cement slurry in the first 2 pages in the 2 marks: slurry density, thickening time, rheology, fluid loss, water content, and composition. We're going to see in detail very brief contents about each and every property. I've already explained to it, but 1 or 2 points could be added here as well. Density is nothing but mass by volume. What density we're talking about? This is density of the cement slurry. Why do you want to take care of the cement slurry density? Is to balance the formation pressure. We're not talking about the drilling fluid, we're talking about the cementing fluid. It also balances the formation pressure with help of a mechanical stability in the control of loss of slurry in weak formation. If there is a weak formation or a porous formation, the cement slurry could be lost, run away. We don't want it, so we want the thicker fluid. What we call it as thicker cementing fluid, high slurry density. And the third point is the heavier the density of the heavier the cement slurry, it could easily displace the drilling mud because these are alternate fashions of operations. One followed first one is drilling fluid sent into the along the drill string and cools the cuttings, cools the drill bit and collect the cuttings. It's we send in successively. The next fluid is summoned is to push the drilling. So the drilling fluid is being pushed by, of course, is a call it as a spacer fluid. We'll be studying next detailed cementing concept. There's a fluid in between the cementing fluid as well as the drilling fluid. First, we send in drilling fluid, and the fluid follows. The cementing fluid density must be thicker than the drilling fluid density for effective displacement of the mud. That is to push, switch, speed, push the drilling mud. So how much could be the density? Should be zero point 0.2 to zero point 0.5 times higher than the mud density to facilitate effective displacement. That means to push, sweep the drilling fluid. Slurry density is measured with the help of mud balance. We have seen the mud balance in the last sessions. We've seen the mud balance in the last sessions, and it will be easy for you to relate to what is a mud balance. Here now we have let me share again the slides. Mud balance is an equipment which gives the specific gravity or the density of the fluid being tested. So for cement, we have pressurized net balance. Mud balance is already explained to you already for demonstration also. So you can make it out what is a mud balance with help of a pictorial representation just like earlier. Mud balance. And here for the cement, we have pressurized mud balance. The reason being there'll be air bubble which is popping up in the fluid and creating error. So to put off this, we will have pressurized mud balance to minimize the size of the air bubbles and so that the error goes down. Mud balance is just balancing the rod for filling the cementing fluid into the specific container cell of the mud balance, and then which is the sliding bar, which is on top of the roller, balanced properly at the fulcrum point. After pouring in the cementing fluid, you'll be able to slide it. Where do you stop it? The indication of the bubble of the view glass or side glass, you'll be able to stay at that point or mark that as a density. And explain the drilling fluid. I explained to you about a lot of pictures in the initial section of the video. You can watch it, play back again, and see the same other concept. This fluid is different. Fluid here is the cementing. So all we say here is the cementing slurry density. The concept Y, balance the formation pressure, control the loss of slurry, which is to fully displace the drilling fluid. Cementing fluid must displace the drilling fluid. So it must be 0.2 to 0.5 times higher than the drilling fluid's density to push or sweep it. And we measure the density of the cement slurry with pressurized mud balance to nullify the effect of errors as well as to nullify the cause of error. Quickening time, we already discussed this before. The time taken by the cement slurry to keep it inside the annulus or the casing in a pumpable state. If it's not into the pumpable state, then there is no use. So if it's not in the pumpable state, then we don't call that as a thickening time. We call that a setting. We don't discuss the civil engineering those will be discussing sitting time, but what we discuss is the time. We want the cement not to thicken. We want the cement to be pumped till the locations, and after that, obviously, it will settle. We want to talk about the term thickening time, which is the length of the time the cement slurry remains in a liquefied state, liquid state, pumpable state at the specific conditions of temperature. So it is referred with 100 Baden units of consistency, and the formula for that is given at the bottom. Expression. Baden consistency is equal to T minus 78.2 divided by 202. So what is the normal thickening time? It is a job time plus 1 hour excess, which is the standard 1 hour excess of thickening time plus job time. Normally, that is referred as the standard thickening time. Time required to pump the slurry into the wellbore safely. So, thickening time is also avoided. Here, confusion could pop in because we define what is the thickening time, and we also say that it could be avoided. Why? What is the condition when we say it can be avoided? Because it causes free water. Once the time for its thickening starts, it causes the free water to separate on top of this column. We don't want the free water to separate because one, if it's letting the cement to separate into free water and cement separately, that means it is not in a pumpable state at all. So if it is going to separate out as water and cement powders settling at the bottom, it's going to create an eddy. Because what we want is a slurry, not separate compositions playing its own mechanisms in the wellbore. So we don't want the cement to settle at the bottom. That's the next point, which can create loss in the hydrostatic head, and it can delay the drilling operations. What is rheology? Rheology, we already came across. What is rheology? Is a measurement or is a science which deals with the measurement of deformation of flow of fluids. When flow is happening, how the form is getting changed. In other words, how the form of liquid or the solids present in the liquids is getting changed. The flow properties of fluid, the properties of cement slurry is very important for the following reasons because it has to displace the mud in the annulus and the frictional pressure losses. Frictional pressure losses while pumping must also be taken care, and the hydraulic horsepower required to place a slurry in the annulus. So these are the three reasons why do we want to study the rheology. This or rheology is nothing but the science of measurement of deformation of flow of materials. So why do we have a friction? Because there is a slurry, frictional pressure loss. What do we mean by frictional pressure loss while pumping? Because it's easy to pump a liquid rather than it's easy to pump a slurry. There, because whenever we have solids being mixed in the liquid, and there'll be a frictional pressure. And when it is lost, it's hard to pump. So that's what will be discussed and studied with help of rheology. Rheology is the viscosity. How is this changed with respect to slurry composition and with respect to time? So that is done by the rotary viscometer, the diagram shown on the right hand side. We already saw it, spring at the top of the dial and the rotor, and there's a spindle cell inside. So when it keeps rotating, we'll be able to measure the rheological conditions. Viscosity, how is it changing with temperature and the slurry concentrations. That's what is called as rheology. We'll be studying this as an experiment in the next year in the linear laboratory. Fluid loss is also being covered for you. What is fluid loss? The cement slurry tends to lose water by filtration. That means, we try to project here the slide what we have to picture. We saw this. This one is APA filtration loss experiment. And this is what is the picture for slurry. Slurry, when there is a slurry means the liquid plus solids present in. And whenever there is a solid present in the liquid, there will be a friction and the friction loss. Yeah. So here, you can see here, The drilling mud is going, and there is something called spacing. We will not talk about it as of now. We'll be doing this in the third unit. Cementing fluid is pushing the drilling fluid. Is pushing the drilling fluid. You can see the red color is the drilling mud, drilling fluid, and cementing fluid is pushing the drilling fluid because drilling and cementing are alternate fashions of business. Okay, you'll be keeping on drilling, and once you see that this depth is attained, you want to just stop with this specific casing, then you'll be pumping in the cementing fluid. There is a fluid which is in between the cementing fluid and the drilling mud. That's called spacer fluid. We'll talk about it later on. There is one term here in the handout which is called hydrostatic horsepower, HP, hydrostatic horsepower, or hydraulic horsepower. You have here hydraulic horsepower. HP formula is H into I divided by 1714. H stands for pressure drop, I stands for flow rate, gallons per minute, and hydraulic horsepower is HP. This is the equation. People could want what meaning on what is hydraulic horsepower? What is hydraulic horsepower? As we covered in the rheology, hydraulic horsepower. And now we are talking about fluid loss. We want a picture for better visualization. What is it? You can see here the drilling fluid, then the filter cake, then the drill formation. Through the filter cake, the drilling fluid can escape into the porous formation. If it is a cementing fluid, you see here, casing, cementing is occupying the outer of the casing and the inside of the well bore. That means that is the annulus here, outside annulus, the last annulus here. So if there are fractures here, if there are fractures or micro channels through which the cement could escape, we call that a circulation loss or deep zones. So for that, we want a good cake to be present here because that will only permeate little fluid cementing fluid to be lost. Then we save more money. The reduction in loss is profit for us always. So this is what we call it as a cementing fluid escape into fluid loss into the porous form. That is what we are talking about in this slide. Fluid loss. Slurry tends to lose water by filtration. Filtration happens and filter cake sits on the well bore and it passes on to the zones. How do we manage it? We add a additive called fluid loss control agents. When you add this additive, the fluid becomes thick and viscous, specifically thicker and doesn't run faster. When it doesn't run faster, so when it doesn't run faster, we don't lose much. Always, there are two chemicals or two schools of thought. One is to make it thick by addition of solids. One is to make it thin by addition of liquids, dilution. So whichever you're going to do it, is going to bring you the eventual result. But many times we'll be playing with addition of food. It's like making a coffee. Sometimes you want a thick coffee, you add more spoons of milk powder, it becomes thick. And you feel that it has become too thick, then you pour hot water again. Chances are the equation goes wrong. It becomes thin again. Then you add one more spoons of milk powder again. The logic is you play with the two to maintain your own consistency. Maintain your own consistency. Better not have the question, why are you adding and why are you adding water or diluent as well as why are you adding powder? Because you have to do both the things to have consistency at hand. Same is the case for coffee. Same is the case for liquid or something. Free water content. What is free water content? It doesn't mean that it is free in monetary terms. Free water means the water present in the cement slurry detaching itself from the slurry and staying it as water. We don't want that to happen. The quantity of water that separates out from the cement slurry in 2 hours. We want that water to be intact with the cement particles, tight, locked with the cement particles, and stay as slurry, stay as a mixture. We don't want the water to separate out as water, pushing down the cement at the bottom. So the time reference is for 2 hours. We don't want that to happen. In the static conditions, wherein the volume of slurry permissible is 1.5 percentage maximum, because excess free water can create water pockets. Water pockets in the cement is separate water pockets, zones, water zones from the slurry. That's not healthy phenomenon. And settling and micro channeling. If water pockets are there, then the solid particles will settle at one zone. Water will be present in the form of a pockets in another zone. We want a slurry. We don't want these two to be separating out in the cement slurry. It's not a healthy phenomenon for us. And micro channeling, small fractures present in the porous formation through which the free water present in the cement slurry could run off. The actual condition is to keep the cement slurry in a pumpable state and as well as in a slurry condition, mixture condition. Mixture or slurry condition means additives, water, cement powder not separating out separately or individually as free water or pure cement settle at the bottom or running away through the zones or micro channel. So this is what is called as a free water content. Last property is the compressive strength. It is a strength developed by setting the cement to hold the casing, and it is to protect it from shock loads and high pressure swelling beyond the high pressure formations. So we'll see how this test is done in industries. The minimum strength for that is 500 psi. Take a 2-inch mold, and cure it for 24, 48, and 72 hours. Means it is kept in the bath at bottom hold static temperature conditions. Once the cement sets, take a 2-inch mold. I repeat, take a 2-inch mold, keep it at the temperature of the reality conditions of the wellbore, bottom hold static temperature, BHST, for this much of hours, 1 day, 2 day, and 3 day or 4 days. It's up to you in the standard ways of doing the business. And then after it is set, you break the cement in a compressive strength machine, then the pressure at which it starts breaking is noted as compressive strength. It's noted as compressive strength. You see the picture to understand it. Here you see, you make a cement mold, and let it settle for 24 hours or 48 hours or 72 hours, and then put it in the cement compressive testing machine. So you want to study it by taking this mold, a cement mold, after it is set for 1 day, 2 day, 3 day, and apply the compressive force. What is compressive force? The force is that squeezes material together, or pushing force applied on two faces of the specimen. Here and here, if you apply pressures, what happens? It compressed and it is the shearing off, it is broken down. So what is the pressure at which things the cement is broken down or sheared upon compression is noted as the compression. That's the compression. So the compressive strength also depends on the water to cement ratio and what is the BHST, bottom hole static time temperature, bottom hole static temperature BST, and time lapse for mixing and placement. That means the time gap between the mixing and pushing. There are three other factors which also affects the compressive strength. One is W by C ratio, that is water to cement ratio, and BHST. Let me correct it. It's not time, it is temperature. BHST, bottom hole static temperature. We are familiar with the word called BHP, bottom hole pressure, which is static, dynamic, and kick BHP also. We'll be covering that as and when it is required. BHST, as of now, it stands for bottom hole static temperature, and the time from mixing and pushing and letting it settle at one specific location. The minimum strength is 500 psi, and how to do the experiment is already explained to you. The units you can play is usually kilonewton. If you want to convert it kg per centimeter squared or into psi, You multiply with these numbers. Better by heart these things. I think there much to explain there. What are the various functions of cement and compositions of cement slurry? Is the next question. You have to uh, watch for the words function and composition. Function means uses, composition means respective contents with respect to values. What is present inside and how much is present inside. Composition of cement slurry. This is a mixture of Portland cement and water and additives. Portland cement, water. What we call it as a Portland cement is a common cement, which is used for concrete, or it's a finely ground powder, which is gray in color, which is burnt and then grinded, which is burned and then grinded. When we come into the Portland cement chemistry, I'll be giving it to you in specific unit number 2, the specific composition of the proteins. Yeah. Cement slurry, it has to have a cement suspension with high water content and relatively low viscosity. That's the basic nature of the cement slurry. And cement slurry, where it is put up, it's in the annulus. We already covered it. Now we have API table here. API, American Petroleum Institute, have classified the cements A, B, C, D, E, F, H, whereas C is called as high early setting cement, high early setting cement, and retarded cement. B is for retarded cement. So class A cement, it's mixed with water. How many is the gallons per sack? 5.2. The slurry weight is 15.6 ppg, pounds per gallon. And it is class A cement, according to American Petroleum Institute, is being referred to a well depth of 0 to 6,000 feet. And BH static temperature, that is BHST, not BHP. It's temperature, BHST, bottom hole static temperature range 80 to 170. You have to, you have to memorize this. Class A cement, according to American Petroleum Institute, is is mixed water is this much, 5.2. The slurry weight or slurry density is 15.6 ppg, pounds per gallon. Well depth is 0 to 6,000. And BHST, this bottom hole static temperature, degree Fahrenheit, 80 to 170. You have to memorize all the tabulated values. Class B, almost the same nature. Class C, nearby values. Nearby values except the mixed water and the slurry weight, which is of different values, but it is treated as a high early setting cement. That means this cement quickly settles. High early strength cement. Class D is a late cement. We don't want to call it as late. Let us say it's retarded. I'm sorry for putting this way. When we say retarded means not properly grown. We come across this word called mental retarded kids. We term them as mentally challenged kids. That means they have a struggle to understand things. So those who are in hospitals or those who are in special care, we call them as mentally retarded. That's not a nice way to put it. A very decent way is called challenged, physically challenged. We should not call it as physically handicapped. We should call them as physically challenged, mentally handicapped. Mentally retarded is a bad word. We will call it as mentally challenged because they have a challenge to they can overcome. So what we call it, that means they will grasp the concepts late. Retarded means late. Class D cement, according to APA, American Petroleum Institute, mixed water is 4.3 and slurry density or slurry weight is that much, 16.4, and depth is 6,000 to 12. You see the depth range, it is differing, and the temperature range at that depth is also different. So E, F, G, and H, you can understand with respect to the well depth and the BHST. The first three being for specifically for the approximately same range of well depth and BHST. The next two approximately the same range for well depth and the temperature. The next one, F, is very unique because It is for reaching the greatest depth, and the temperature is also, it can withstand 230 to 320 G and H accordingly. Typical composition of APA class of oil well cements. We have APA class A, B, C, D, E, and H. For E, G, and H. F is missing here. There is no specification about F here. How much is present? So please see here composition. What is the question? Functions as well as composition. So composition means the compounds present with values. So if APA class meant A, class A, class B, class C. A is 53% C3S, 24% C2S, 8 or 9 or 8 plus percentage C3A, and 8% C4A. The rest being phases, usually calcium sulfate. This, the fineness is 1500 to 1900 centimeters squared per gram. So this is for A. This is a value for B, C, D, E, G, and H. The F slab is missing here. So you can make it out. If at all, this is the class A cement, according to American Petroleum Institute. And this must be having this much of C3S, this much of C2S, this much of C3A, this much of C4A, and the fineness, the powder fineness must be this much values, minimum to maximum. You have to by heart it. That's it. But I have to tell you what is the C3S, C2S, C3A, C4A. Okay, which is very simple. Tricalcium silicate, dicalcium silicate. Okay, and we will, if I share you the slide, it will be easy for you. I put a picture here. And the other references you can see here. So this C3S, C2S, same table. F is missing here. C3S, C2S, C3A, C4AF, and the last one which is missing in our handout is CaSO4. Roughly, if you add all these things, it should make out 100. Okay. High early strength. High early strength is achieved by increasing the tricalcium silicate. Better retardation is by controlling the C3S. If you reduce the C3S, where is C3S? You see C. C is what is called as high early strength in our nodes. C is high early strength. By increasing, if you look at all the C3S, this stops the value 58. So if you increase the tricalcium silicate, then American Petroleum C class will be fine. If you add this more, then it's called class C cement. If you bring that to least, it's called class B cement. So if you want a better retardation, that is D, then D, you will be going for C3A and C3S and C3A. You will control both these two, this and this one. Bring this and this less, it becomes class B. Low heat of hydration, then you will say D and E is low heat of hydration. That is by limiting the C3S and C3A compounds. Both this value and this value. And resistance to sulfate factor, that is achieved by limiting the C3A. If you limit the C3A, the least, let's become class G cement, which is the least value C3A. If you reduce this, then it becomes class G cement, which is nothing but it is the cement which is resistant to corrosion, resistance to sulfate. So all this is explained, but again the basic doubt would come: what is C3S, C2S, C3S, C3A, and CaSO4 is easy for you, calcium sulfate. For that, I put this slide here. What is C3S? Let's go from right to left. C3 means 3 of calcium oxide and 1 of silicon dioxide. 1 is missing here. We can miss it out. That's what I in fact says. Not necessary to write 1 here. So how much is the calcium part? 3 times of calcium oxide and 1 time of silicon dioxide. C2S, what is the meaning? 2 times of calcium oxide and 1 time of silicon dioxide. What is C3A? Please see here. It's not SS, now it's changing to A. So 3 times of calcium oxide and 1 time of aluminum trioxide. Okay, that is aluminate. Tricalcium silicate. Look at the names. Tricalcium aluminate. Dicalcium silicate. Tricalcium silicate. The last one is called tetracalcium aluminum ferrite. Tetra 4 calcium aluminum ferrite. That means 4 CaO, 1 Al2O3, and 1 Fe2O. That is called ferrite. Low heat of hydration cement, highly early setting cement. So fastest hydrating and resistance to corrosion and slow reacting cement. So if you add these more, you get this property. If you add this more, you get this property. If you had this more C3A, it quickly settles. This one quickly settles. If you want low heat of hydration, that is when water is being added to cement, if more heat is wanted, then you don't want that much heat when hydration is happening, then you have to choose the cement, which is called C4AF. Let's go back to the slide to understand C4AF. Okay, that's the logic behind the cementing API glass cements. American petroleum industries. High early strength by increasing the C3S and grinding fine. Better retardation by controlling the C3S and C3A. Explain all this to you. Low heat of hydration, that is D and E1, is achieved by limiting the C3S and C3A. You can see here in the same table also C3S and C3A. Sorry, C2, C3S and C3A. Yeah. C3S and cementing C3A. You reduce this, then it becomes D and D class cements, that is low hydration heat or low heat of hydration. And by limiting the C3A alone, you will get resistant to corrosion or something. So if you reduce this, then you'll be able to get resistance to sulfate or corrosion. So let's move on to water drilling fluids. I think this section is already familiar for us. And let me share other slides with you. I believe you are able to see the next one. What are drilling fluids and what are its functions? This is what we're going to talk about. I think this is more of a repetitive. Let's quickly go through the contents. Drilling fluids are fluids used in the drilling of underground wells for successful drilling out of the wells. And it is another name. The way of calling is called mud or simply mud. Skipping the first paragraph, let's get into the role of fluids and their impact on drilling of the health of the well. Is to transport the drilling cuttings to the surface, it exerts hydrostatic pressure, and to increase the wellbore stability, to prevent the whole collapse, and to shale destabilization. Drilling operation exposes the producing formation to the drilling. So, and any solid chemicals contained in that fluid is also going to create a damage. So drilling fluid is used for holding the drill bit, collecting the cuttings, maintaining the hydrostatic pressure, stopping the kick, balancing the formation fluid pressure, and enhancing the fluid well booster. These are the basic functions which you already know about. So taking this time to switch the slides. I made it as separate PDFs while I'm highlighting the context. Okay. You could have a question here. Drilling operation exposes the producing formation to the drilling fluids. When there is a producing formation and when you're drilling it, the drilling fluid is getting exposed to the further newly created formation. zones where there could be micro channels or fractures there, then these cuttings could escape through the micro channels and further create a clogging or a blocking, what we call as a stream of information damage. There could be a possibility also there. When you read this content, longer runs, you can play the video. What I'm saying here, if you superimpose the logic that I've said, it will be easily understandable for you. Switching the slide to another one. Bit and the drilling string. The bit and the drilling string rotate at relatively high revolutions per minute. Here we have to come across with two uh, concepts. One is rotation and another one is revolution. For that, I put a picture here. Rotation to spin on its axis. Okay, to spin on its axis, and revolution to travel around another object. Travel around another object. This is a classic definition which we studied in school science or geography. Earth sciences to understand what is the difference between rotation and revolution. Rotation and revolution. We are now we back to the handout. The bit and the drill string rotate at relatively high RPM means rotations per minute, but we are talking about revolutions per minute, REV divided by MIN. This is the unit. The drill bit and the drill string rotate at relatively high RPM. Okay, so when we talk about drill bit, we will be talking about RPM, and now we are talking about drill string as well as the drill bit. So we have to notate it with two terminologies. One is RPM, another one is REV divided by MIN. It is revolutions per minute. The circulation of the drilling fluid through the drill string and up through the annular space it helps reduce friction and cool the drilling string. So when the drilling fluid goes in, it goes in. But we have not talked about cooling the drill string. It also cools the drill string. It also helps reduce the friction in the drill string. So when there is a rotation force, when there is a torque of the drill string is also being cooled by the drilling fluid and the friction because all the time the fluid is washing away. The fluid is washing away the drill string as well as the drill bit. So far, we have given too much emphasis to only the drill bit, but it is also for the drill string. That is what we learned in this lab. Drilling fluids provide more information of the well bore because it's a representative sample of the geology. That means whatever raw cuttings comes to the surface, you can study the surface, uh, you can study the subsurface with help of the cuttings what we would find. So drilling fluids is able to collect the raw cuttings. So the raw cuttings are nothing but representative sample of the population. So for example, if you're cooking and to check whether the rice is properly cooked, you will put back a ladle and then a spoon or a ladle, and then you will take two or three times at different locations and then check the rice whether it's properly cooked. If three rices are properly cooked consistently, then you make a conclusion the rice in the whole vessel is cooked properly. A sample is representative of the population. That's what is called statistics. So when you collect raw cuttings which are being collected by the drilling fluid, it is going to tell about the reservoir subsurface. So what we test here. Drilling fluids, nature or property. Drilling fluids minimize risk to personal, environment, and drilling equipment. How come? If the fluid is going to ensure well-bore stability, then there is less accidents going to happen, minimized risk to personal and environment drilling equipment. But of course, it has to be daily tested and continuously monitored by the qualified person. Drilling fluids by a qualified person. Let me switch on to the other slide here. The next half of this. Depending upon the location of the well, the drilling fluid systems can be exposed to salt water flows, influx of carbon dioxide. That means where the uh, drilling fluid and what sort of problems could pop up. Location of the drilling fluid and what all the problems the drilling fluid could face. Depending upon the location of the well, you can have salt water flowing in and you can have influxes. What is kick? Kick is nothing but influx of well fluids, oil, gas, and water coming out quickly. I'm not able to highlight the second point, which is also important, very important. I think here it's taken as an image rather than text. So I'm not able to highlight the second point. I'm talking about the second point. It's influx of not well fluids. Influx of well fluids is called kick. All of a sudden, oil, gas, and water coming out is called kick. If it is turning into blowout, we have to use blowout preventer to manage it. Before it, we can use up, we can create procedures to manage it. Influx of carbon dioxide and hydrogen sulfide both are equally corrosive in nature. Hydrogen sulfide is a gas which is highly corrosive, but carbon dioxide is also equally treated as a corrosive gas. So both these gases are corrosive in nature, and if it comes to it, this is a highly risky uh, thing for the drilling fluid system. And if too much of solids is going to build up, again, it's going to risk. Oil and gas influxes, yes, it's also a restful drilling system. So that is why we import hydrostatic pressure to stop. So throughout the well construction process, the drilling fluid man, the engineer has to accurately record the test results, calculate the fluid volumes, how much the drilling events, successful events, what step by one, step two, step three, and plan for the inventory. That means how much chemical he has to buy, what are the additives, and how much cement for cementing fluid, how much is the bentonite or clay, weight adding, galena, viscosifiers, what all you have to add as additives and make out the drilling fluid. Then he has to have a stock of all these things, product inventory, and environmental compliance. You should also make sure that he's not polluting the water. So that's it with respect to this question, the functions, drilling fluids functions and its role and impact on health of a well. That's the last portion, which is minimally covered here, health of the well. The health of the well, but also means the health of the person involved and the public involved. So we covered up to here, and we'll be moving on to the next question. Hi all. Now we are into the question. Give the composition and related properties of milk fluids. The combined question. So you want to answer this question, and you can make out two structures. One structure for drilling fluid separately, and one another for cementing slurry composition properties, or you can combine both and then you generate information. Composition of drilling fluids. Basic composition is more of repetitive in nature because wherever repetition comes, it is because we already covered. The basic components of drilling fluid are viscosifying agents, the chemicals which increase the viscosity. Examples are clays, polymers, and emulsifier liquids. We know what are emulsions. Emulsions are oil and water and oil. So what's its nature? It's to thicken the mud and increase the whole cleaning ability. So what do viscosifiers do? Viscosifiers are chemicals which are added to increase the viscosity to make it thick and to increase the whole cleaning ability. How do we say it's whole cleaning ability? We know what we use for home purposes. Prill liquids, prill vim bar liquids are used for washing. So viscous fluid, mostly made of lemon for washing the vessels in the kitchen, is used for better cleaning of the plate. Limy surfaces can clean the oily surfaces, the oily stuff surfaces, the surfaces. So that's a typical example in the kitchen, which can be superimposed to the oil industry, where use of viscosifying agents can be mm, used to increase the efficiency of cooling by adding viscosifiers, which can thicken the mud and also clean the drill. Weighting agents. Weighting agents are chemicals which are added to increase the weight of the density and thereby stopping the kick, balancing the formation pressure with the help of hydrostatic control the subsurface pressure. The chemical is called barite. The spelling there for barite is B-A-R-I-T-E-S. Let me repeat it. It's B-A-R-I-T-E-S. Barites, hematite, magnetite. We saw the formula of all these things in the initial classes. Barite here is BaSO4. What's the specific gravity and the hardness? Specific gravity and the hardness is given there. Barite, BaSO4, chemical formula, specific gravity and hardness. You can have the values. Or in specific, you have to give the percentage of these chemicals present in any one of the organizations. Well, I have put this in the additional unit handout, which have circulated to you in addition to the existing material. So what are the chemicals present, how much it is present, and in percentage. Hematite, Fe2O3, respective values. Magnetite, Fe2O4, galena, lead sulfide, limonite, TiO2, and siderite, FeCO3, silicide, strontium sulfate, SrSO4. SO stands for strontium. Z value atomic uh, number 38. Dolomite, calcium carbonate, magnesium carbonate, further calcite, calcium carbonate. All these chemicals are added uh, as weighting agents. All these chemicals are added as weighting agents to increase the weight of the vegetable, to stop the kick, to balance the formation pressure, exerting a hydrostatic dispersants or deflocculants. Dispersants, the chemicals which are used to scatter, the chemicals which will not settle at the bottom quickly, which will be held in suspensions. Deflocculants, flocculants meaning the ability of material to join together and begin a bigger mass. Deflocculants is opposite. It's a chemical which is added to mm, not let it to join and become a bigger mass. That's one is called deflocculant. Drilling fluids. The drilling fluids, dispersants or deflocculants are added to thin the mud and reduce the surge and swab as well as the circulating pressure problems. I've already explained to you what is a surge and swab pressures. Let me share a PowerPoint slide so that you'll be able to understand. Here is slide for surge and surge effect. So surge and swabbing effect. So what is surge? Surge is actually BHP increase. BHP increase when the drill string as well as the drill bit goes down. So when the drill string is going down, what is the change in the resulting pressure at the bottom? What happens to the BHP? When the BHP, what happens to the BHP when the drill string goes down? When the drill string goes down, the BHP increases. That's called surging effect. When the drill string goes up, the BHP, the bottom hole pressure, decreases. That's called swap. So there are two phenomena in oil and gas industry. When the drill string goes up and drill string comes down. When the drill string goes up, the BHP reduces. That's called swapping effect. And when the drill string comes down, The BHP increases. That's called surging effect. Pressure changes because of the drill string going up and down. Specific pressure, what we deal with is BHP, bottom hole pressure. That's what is called surge and swabbing effect. I have written this in the additional notes also. Going back to the material what we have at hand, filtration loss reducing agents, the clays, polymer, starches, and dispersion. Starch is nothing but a white granular organic chemical that is produced in plants or by plants, which is used to add thickness and as well as let it not to thickness consistency, let it not to thin and run faster. So like clay, the starch is also, for example, the starch what we put for stuffing the uh, chemical onto the dress material so that it looks very stiff before ironing. So starch solutions, we buy starch solutions and prepare it in water and then soak the shirt. And then after drying it up, when we iron it, when we press or iron it, what will be? The material looks very stiff. The material looks very stiff. That's a starch. All the plant extracts powders are also examples for starches. The starches, clays, polymers, dispersants are being added. Sometimes asphalt, tar material also to reduce the filtration loss of the fluid with the borehole. This is done in an intention to reduce the formation damage, differential pressure sticking. We already know what is differential pressure sticking. Let me share the picture so that it's easy for you to explain. Here, you know what is the hydrostatic pressure, the formation pressure, and what happens to the filter cake. It is formed on the surface of the borehole. What happens to the drill string here? You see, it goes and sticks to the sides of the well bore, sides of the well bore. So here you can see the plan or the top view of it. The drill pipe. The drill pipe is not at the center. The drill string is not in the center. It is off its location and sticks to the furnace. This concept is called differential pressure sticking in this case. Okay, differential pressure sticking. So when you reduce the filtration loss with help of filtration loss reducing agents by addition of clays, polymers, starches, and dispersants, you'll be able to reduce the formation damage as well as the differential pressure. What's caustic soda? It's a new way. It is added to increase the pH so that it reduces the corrosion and performance of the dispersants. Salts are also added to protect the downhole formation or to protect the drilling mud from contamination because of formation water. Sometimes it's also used to increase the density. So salts is to protect the mud from the formation water. The second has got a second function, so also used as a weighting agent. Is also used as a weighting additives. The other additives are lubricants. We know what are lubricants, corrosion inhibitors, and preservatives, bactericides, and emulsifiers, chemicals which are added to increase the emulsion nature of the fluid, temperature extenders. These are other additives which are added to the drilling fluid. Properties. Properties of drilling fluid. You know what? Why do we need to study the properties? We need to know the functions of each and every additive which is being added to the drilling fluids that it performs well. It performs well down. So there are a particular range of values for these parameters. I've tabulated one of the fluid functions, and its composition from one organization. So this is also put up here. You can see in the PPT. This slide shows how much of water is a base fluid and deformer, antiforming agent. how much is being added. And soda, ash, what's the function? zero point 0.5 pounds. Potassium hydroxide is for pH control. Bentonite or clay is for viscosifier. Gum, xanthan gum is for viscosifier. Natural xanthan gum, and from trees. Starch for fluid loss control, 6 pounds. And polyacrylamide, 1 pound. Potassium chloride for clay stabilization. Calcium carbonate, low circulation material. Barite is a weighting agent, and perlite is an anti-sagging agent. So all these chemicals are added to the drilling fluid, base fluid water with respect to this one. So look at the heading, drilling fluid composition of one organelle. This is also copied to you in the handout in the additional notes. You can relate to it for this question. Okay, you can relate it with uh, the system of values for this. That's how you have to answer for the question. Functions is easy, properties are easy, but when you're talking about composition, the contents along with the person. So particular range of values for these parameters are just the physical and chemical properties. What is the density? Weight per unit volume. Final viscosity, we've already finished. The number of seconds required for a given flow to flow 1 quart, 1/4 of a gallon into a graduated cylinder through the funnel orifice of standard dia. I already explained to you what is a funnel viscosity. Watch this section of the video, you'll be able to understand. Filtration properties, we already covered it in this slot. It's about APF filtration test. I posted the diagram too there when before explaining. pH, self-explanatory. Fresh water, bentone clays get dispersed and performance in alkaline pH range of 8 to 9%. 8 to 9. So why pH? Because if it is acidity, it is going to create more corrosion. It is going to affect the other systems, chemical system, mechanical system. So we will always maintain it in the alkaline range, 8 to 9. Other properties, alkalinity, there's now covered it. Cation exchange capacity, I've given a video explanation. Link the technical link from Stamberger glossary and another reference. I've already posted a picture. And what is the use of having a cation exchange capacity? In the picture, I've highlighted what is the use there. Why is it used for deeper wells? Electrical conductivity, it's simply to measure the resistivity of the filtrate, and lubricity, name speaks, ability to lubricate and reduce the friction and absorb the heat. So that's it with respect to base material, the handout which is given to you. Now we'll be going on to the additional units. Still one content is pending, that is this portion. Explain the functions and properties of drilling fluids. We started here, subsurface pressure control. We talked about kick. Kick is influx of any oil well fluids, any well fluids, oil, gas, and water at any high pressures. It will come out with big force, and chances are the surface above will cave in or pour in at the same time. If it's in unconsolidated formation above, it's a loose formation above, and the whole wellbore could collapse. So either kick or kick along with giving in happening is a disaster in industries. So for that, we have to supply hydrostatic pressure to match the subsurface pressure. That's what we talked about in subsurface pressure control. And the reason why, because when the balloon is opened, the air starts to expose the atmospheric pressure and releases from the balloon. Same is the case with the formation. When there is hole is made, the hole is exposed to atmospheric pressure, and the valve will start ejecting out. This ejects out higher pressures and force, what we call it as a peak flux of valve fluids. And if it is higher than the range and if it's uncontrollable, it becomes a blowout. Let that blowout let not be turned into a fire disaster. That's why we have mechanisms, technical procedures, and as well as deal with this. So how do we calculate the hydrostatic pressure? Pressure is equal to Dvd into density into through vertical depth multiplied by rho, density of fluid, and g. So that's the formula for pressure. We need to keep the well stable and it should not collapse. Cutting, removal, and transport. This is the next function of, yeah, we know about it. Little bit extra information here. The circulation of the drilling fluid causes the cutting to rise from the bottom of the hole to the surface. So what do we talk about efficiency of the drilling fluid? It's one of the best function of a drilling fluid is to cool the drill bit, collect the cut. So efficient cutting removals requires circulating rate. If the circulating rate of the drilling fluid is not maintained, what will happen? The forces of gravity, because of the force of gravity, it will tend the cuttings to go down, to slip and reach the bottom and settle there. Then as a result of it, we will be having drill bit balling. Drill bit balling is lot of mud, lot of thick mud, the solid portions of the drilling fluid, mud itself, sticking to the drill bit and giving a ball effect, giving a ball-like effect. That's called drill bit balling. So the other factors which could affect it is of fluid density, rheology. We talked about rheology, the deformation of the signs of deformation of material, or especially of a drilling fluid or a slurry or cement slurry. How does the viscosity change with respect to time? Is my own take on it. Rheology, the angular velocity, the velocity of the fluids in the annulus, the whole angle, and the cutting slip velocity. How far it slips and reaches the bottom, and so that it becomes a little bit boring. One of the possibilities could be little bit boring. There could be other possibilities also. Suspension of solid particles. We discussed gelatin as an example here, and cough syrups also as examples for local funny examples. We can superimpose the same logic with drilling fluid. Suspension of solid particles. The circulating mud pumps have to be stopped. Here is a reason why we need to keep the solid particles in suspension, because not always the drilling will happen. It has to be stopped for some reasons. What are the reasons? During connections, when you want to connect the drill pipes, during trips or downtimes. Downtimes means there is some maintenance required in the well. We have to stop it. At that time, what happens if all the solid particles along with the cuttings do go reach the bottom and settle there? You will not be able to let the rotating effect happen in the drill bits. So that be a challenge there. Okay, so you cannot let that much turbo force to start again. So it's better viable option is to add these suspension agents and keep the chemicals on the rock cuttings in suspension and hanging in movement always. So if it is not removed from the hole, then it must be held in suspension. Otherwise, what will happen? They'll fall to the bottom or into the deviated well, low side of the deviated well. What do we mean by low side? When the wells are bending, then at the bend portion, if the rock cuttings are settling, then sooner or later the erosion happens. The erosion happens to the drill string, and chances are arc, and then tensile force, compressive force, and talk along with it, drag, all these put together would result in a drill string collapse possibilities there. So we need to choose a suspending agent, the chemicals which will keep the drilling fluid in a jelly form, gel quickly and hold the cuttings in suspension. Cuttings will be in suspension, hanging, freely moving. It will not settle at the bottom. So this is what we call as a thick-saw property. I have defined to you what is already thick-saw property. The reduction in viscosity of a fluid upon applied stress is called Sealing of permeable formations. When the drill bit penetrates the permeable formation, the liquid portion, what happens of the drilling fluid, reaches the cake and get filtered into the formation. So what we call it as a filter cake is a solid portion of the drilling fluid which is settling onto the borehole through which the liquid passes on. And it's not an advantage for us. It's not an advantage for us. The liquids slowly getting lost in the micro channels of fractions. It's in fact lost to us. So that is what we call as circulation losses or loss of rate. So it happens most of the thing in a permeable porous formation. So here there is a spelling mistake here, relatively impermeable. Okay, the cake must be thin and it must not permeate. So if you're having a drilling fluid, we say it's a good drilling fluid, it has to form a thick cake or a thin, which is thin cake, which is impermeable. If the cake is not permeating, filter cake is not permeating the fluid, then we don't lose money at all. We don't lose money in the sense a lot of chemicals which are being added. We studied galena, barite, viscosifier, so carboxylic cellulose, all these chemicals which are being lost in the long run in the microchannels or especially in the low circulation zones and feed zones. Then money is managed. Well. Money is not running good, then money is managed good. Here also, the filter cake is not impermeable. What for the spelling mistake here? It is not impermeable, then more of the liquid will invade into the form. If it is not impermeable, two negatives. Cancel out the two negatives. English writers, basic speakers, they don't use two negatives here. They will directly write permeable. If the filter cake is permeable, if the filter cake is permeating, what will happen? Lot of liquid will invade into the formation. Go, invasion, cross the border. That's the meaning of invasion. Cross the border and get into the formation. If that is happening, then loss of money. That's all. So the thin, low permeable filter cake, a tough filter cake, then success is the filling fluids function and success is the filling. Polymers are also used for this additives, used for this reason as an additive. Stabilizing the well bore. The borehole, once drilled by the bed, remains stable. Till the casing has to be, till that portion of the well is drilled and the casing lowered and cemented. So when do we need to stabilize the well? Here is the answer for that. Well bore stability. You know what is a drilling? Drilling happens. It must be kept stable till you fix casing and cementing. That is the meaning. Or until that, the safety is not guaranteed. Safety is not guaranteed. You drill a hole, you try to take away the cuttings, and then we put on casing and cementing. Before putting casing and cementing, then you will have to stabilize the well bore. There are two ways in which you do it. One is mechanical, other one is chemical. Here will be discussing chemical. The density of the drilling fluid is so adjusted that it exerts HSP hydrostatic pressure to keep the peak under condition and the well bore stability under control. The borehole instability is happening as a result of the drilling fluid reacting with the shales, reacting with the loose shales, the rock, the formations which is taking. If it is reacting, then the fluids can go into the formation, the fluids can come into the formation can get dislocated, or it can slough, what we call it as sloughing of fluids. The properties of drilling fluids, which is already covered to you. So this is suffice with respect to the waste material, the handout which is already given to you. And now we are moving on to uh, the new added material or additional nodes. Give an account on the overall drilling fluid benefits. What are additives? Basically, additives are chemicals added in smaller quantities to better the properties of the main. For example, when we make tea, if we add a powdered form of cardamom to the tea, you can call that as a additive. Elachi chai or cardamom, which is being powdered carbon, which is added to the tea, could spice up the tea, could add flavors to the tea. So any material which is added in smaller quantities to the base fluid or the main fluid in this for the sake of betterment or to increase the efficiency to enhance the properties of the main fluid is called an additive. So what additives which are being added to our drilling fluid is alkalinity control additives. That means pH. These additives are to regulate the acidity or basicity so that you will be able to have fluid stability. Examples are magnesium oxide, potassium hydroxide, and sodium bicarbonate. Corrosion inhibitors. Corrosion inhibitors are the chemicals which are added to prevent the corrosion, stop the corrosion, mitigate, neutralize the acid gases. Acid gases are H2S and carbon dioxide. These two gases present in the well fluid, which can be result of corrosion. So, in fact, to neutralize these hazardous acid gases, we'll be adding corrosion inhibitors. Once the corrosion is stopped, the drilling tool and the drilling string failures can also be prevented. What are the chemicals for that? Organophosphate and trinsoluble amine. These are added as a corrosion inhibitors. Defoamers. Defoamers, the name itself speaks there. The chemicals which will reduce the foam. So the chemicals which are able to reduce the foaming in drilling and completion fluids, to control foams and to air entrapment while maintaining environmental acceptability. That means too much of pollutants which are being added to the environment. If at all you are using defoamers, it will take care of it and it will control the foam happening in the drilling. Sometimes foam is itself a drilling fluid, which we'll be talking about in the next. Alcohol-based defoamers, emulsifiers and wetting agents. The chemicals which are added to increase the emulsion nature of the drilling fluid. Emulsions, we know what? Oil in water, water in oil is also called emulsion. To create a stable emulsion between two insoluble liquids. Emulsifiers which are added are diesel, mineral oil, and paraffins. It also, these wetting agents, the chemicals which will wet and keep the cuttings oil wet always, not water wet, oil wet always to have a slimy surface, to lubricate it and to keep always the water content be present there because a little bit of oil is going to keep the water present there for longer time. So it's just to control the rheological properties and fluid loss control. Do not assume that emulsifiers and wetting agents will only work on creating an emulsion, creating a wetting coat. Wettability is the ability of a fluid to coat the surface, to spread and coat the surface. It's not only for that, it is for, despite after doing the job of emulsion stability, it has to take care of rheological properties and fluid loss control. That means emulsifiers and wetting agents will also do the job of fluid loss control and take care of the rheology. Rheology is the kinds of what do we say? Signs of deformation of an object. Filtration reduces the chemicals which are added to uh, let the filtrate under norms, means there should not be loss of filtration across the filter. So it will reduce the fluid filtration of water based drilling fluids, especially at high pressure and high temperature conditions. Example up to 500 degrees Fahrenheit or 260 degrees. LCM stands for non-mathematical LCM. LCM stands for in oil and gas industry. In short, we call it as LCM, loss circulation materials. That means the chemicals which are added to minimize the loss circulation in source. What is loss circulation? The drilling fluid or cementing fluid running through the micro channels or fractures to an unnecessary location, to an unnecessary location. The necessary location is the annulus. It has to pass through the annulus and come back to us. When it is not coming back, it is getting connected to an existing micro fractures or channels, and it is lost. It's all loss accretion materials. The whole aperture size is 1 mm or greater. A lot of LCM is formula hidden there. So formula hidden there in the sense is kept most of the time secret by the confidential by the India oil and gas industries. What's all low circulation materials are being added, but generally you can dig it out from the research documents what LCM materials are being circulation materials. What low circulation material is given in the typical example. What I provided you is a calcium carbonate. It's a calcium. One of the examples. Lubricants, name itself speaks, studies the friction and the drilling strength, and to take care of dark, drag, stuck pipe, and to increase the rate of pipe. Pipe freezing agents. So when the drill pipe is stuck, differential pressure sticking. When the drill pipe is differentially stuck, we have to use some gellants, diesel oils to free it. These are called pipe freezing agents. Shale inhibitor. What happens if the water-based fluid is reacting with the loose shale? So you'll have to improve the well stability by adding the shale inhibitors that will increase the viscosity, and flocculate the drill solings and encapsulate. Encapsulate means cover the cuttings. Encapsulates the cover the cuttings so that the cuttings are not reacting with the shales. The cuttings are not reacting with the shales. Surfactants. Surfactants are soap solutions, which is for reducing the interfacial tension between water and oil. Temperature stabilizers, the chemicals which are added to increase the rheology and the filtration property to enhance the wellbore stability, what we call as rheology, viscosity with respect to time, change of viscosity or the deformation with respect to time. So stabilizers which are added to keep the viscosity and temperature under control is called temperature and viscosity stabilizer. Thinners and dispersants. It's for reducing the rheological properties. Thinners. Active clays by dispersing the active clays and drilling solids. Viscosifiers we already dealt with. It is for cleaning and the base material what we've circulated already. The handouts. We have dealt in viscosifiers and weighting agents in detail. Viscosifiers are chemicals which are added to keep the solids under suspension, which also to better the cleaning, whole cleaning. One such example is carboxymethyl cellulose. And weighting agents, we had a table there, barite, a lot of chemicals, magnetite, hematite, all these chemicals are added to increase the weight or the density, and so that you can stop the caving in and to help dry pipe pulling. That's the two logics there. This is what I've copied down. I've already posted in the PPT. So water, it's a base fluid. How much you had? zero point 0.7 barrel. So zero point 0.7 barrel. If you look at the rest of the chemicals, you can see soda ash for maintaining calcium concentration, 0.5 pound. 0.5 pound, okay, for barrel. This is basis for 1 barrel. Of 1 barrel, 0.7 is water. Only zero point 0.3 is the rest of the chemicals. So of the zero point 0.3 barrel, what are the chemicals added pound basis, weight basis, because the rest are all powders. And the first one, water, is a base weight of barrel. Foamer, anti-foaming agent, 0.08 pounds. Bentonite, 4 pounds. Xanthan gum, 1.5, so on and so forth. I've explained to you the same table I copied down. What is a TUMAC? Cation exchange capacity and electrical conductivity is already dealt. I've given you special 3 links for understanding cation exchange capacity. Please follow them. Additives already explained to you. Loss on ignition, explained to you again. It's the vigorous heating of a sample at a temperature till all volatile escapes until moss stops changing. I explained the scale in the class, and then I've informed the class that I've penned it down and not necessary for you to copy down during the class. So less of dictation. Here is the definition for loss of. loss on emission. When you burns a fluid, when there is no mass change happening, or when all the volatility components are escaped, then that is called remains is called loss on emission. Thickening time, the time, the duration where cement will remain liquid for pumping. The pump, sorry, the thickening time is nothing but the time of the cement slurry to remain in a pumpable state. That is what we discussed. Geology, science of deformation on flow of materials. Free water content, let me say it's not free. It is the water coming out of the cement slurry and staying away from the slurry as a pure water. And that is what is called as a free water content. Compressive strength, I showed you the picture, and short meanings of caving in, kick, exotropy, surge and swap. All these concepts are explained to you in my explanations, be it in the drilling fluid or well drilling subjects. You guys know what is caving in, kick, exotropy in this subject, less viscosity, viscosity getting reduced with respect to applied stress, surge and swap pressures. What happens when the drill bit goes down and drill bit comes up? The pressure changes are there and it is given up here. Give meanings of RPM, revolutions per minute, and flux. Additional information are put up here. Basic ones. We asked in university examination flux, even if it not, it is an interview question. What is a flux? Any quantity with respect to time and area is called flux. So that's it with respect to unit one. And let's meet again.